Alright, welcome back everybody. Today we are kind of expanding on Coulomb's law, but we're going to be talking about superposition. So often there are many electrical charges within a given area. They may attract or repel from each other. You can find the net charge from all these charges by combining the forces from each charge. So for example, let's look at this. We have charge 1 over here, and this charge it's going to be feeling a force from charge 2, charge 3, and charge 4. And the way it's going to move, or the net force, is going to be a combination of all of these. So for example, 4 is going to be pushing it this way. 2 is going to be pushing it this way. And 3 is going to be pushing it this way. And if you add them all together, so this is coming from 4, pushing this way. This one's coming from a 3, pushing this way. And this one is coming from 2, pushing this way. What you get is the combination will give you this net force of all of this. If you guys remember vector addition, it's kind of like using vector addition. I know we won't be really doing vector addition for this, but that's the idea of it, okay? So you can find the net force by finding what the force is by each of those other charges that are around it. All right, so let's try some examples here. Conceptual example, number 11, superposition. Looking at the diagram below, there are 3 particles with the same magnitude of charge. Charge Q1 is located at their origin, charge Q2 is located 1 meter from the right of the origin, and charge Q3 is located 0.575 meters to the right of the origin. Which charge will exert the most force onto the positive charge Q3? Q1 or Q2 or both? And pause it if you want to think about it. So you might be thinking, because they all have the same amount of charge, don't they exert the same amount of force? But then you need to also think that this charge over here, Q2, is a lot closer than this, so it exert a much larger force than Q1. Okay, moving on. Looking at the diagram below, there are 3 particles with the same magnitude of charge. Charge Q1 is located at the origin. Charge Q2 is located 1 meter from the right of the origin. Charge Q3 is located 0.75 meters to the right of the origin. Which direction will the positive charge Q3 start to move? Okay, so we're wondering which way is this going to start to move? Well, we can kind of think about the forces acting on this charge Q3. So we know Q1 is going to be trying to attract it. So it's going to be trying to attract it, pulling it to the left. Charge Q2 is also going to try to attract it, and it's going to be pulling it to the right. And one thing we should know is that since charge Q2 is closer than Q1, and they both have the same charge, that means this force is going to be a lot bigger, meaning it's going to start moving to the right. Okay? All right, moving on. Or I should say it's going to start accelerating to the right because there's a net force to the right. But anyway, yes. Example number 3. Okay, so first mathematical example, and these they're not hard, but just tedious and takes a lot of time. So a charge Q1 is equal to -5 coulombs. So let me just write that down, -5 at the origin. And charge Q2 is equal to -2 coulombs, is 50 meters to the right of the origin. And charge Q3 is equal to +4 coulombs, which is located 40 meters to the right. Okay, so let me see. 40 meters. Oops, 40. And this one is 50 meters. Okay. Find the magnitude of the force between Q1 and Q3. So we're looking for this force right here. This one's going to be attracting it to the left. So we're looking for that force. So I'm going to say F31. And we're using Coulomb's law. K Q1 Q2 over R squared. All right, so let's see. F31 is equal to K, which is 9 times 10 to the 9th. Charge 1, which is equal to 5, the absolute value. Q3, which is equal to 4. And how far are they from each other? 40 meters, so 40 squared. I put it into my calculator. 9 times 10 to the power of 9 times 20 divided by 40 squared. and we get something like 1.13 times 10 to the 8 newtons. Okay, so that's what the value is going to be of this attractive force that's pulling it to the left. Okay, now we're going to find the magnitude of the force between Q2 and Q3. Okay, so this one is going to be pulling it to the right. Okay, so I'm going to do F2 or 3.2, and that's going to be equal to the K constant, 10 times 10 to the 9th, Q2, which is equal to 2, and Q3, which is equal to 4, and divide that by how far they are from each other, and that's going to be 10 squared. All right, let's see what that is. 9 times 10 to the power of 9 times 2 times 4 divided by 10 squared. And then we get something like 7.2 times 10 to the 8th. Okay, so part C asks, find the net force on Q3. So both charges are going to be pulling it towards each other, and we want to know what the net force is. So the force net is going to be equal to the force that's pulling it to the right minus the force that's pulling it to the left. So we have 1.1. Oh no, sorry. F32 is going to the right. So that's going to be 7.2 times 10 to the 8th minus 1.13 times 10 to the 8th. And let's see what we get there. 7.2 times 10 to the power 8 minus 1.13 times 10 to the power 8. And we get around 6.07 times 10 to the power of 8. Okay? Hope that makes sense. I know that was a lot. I don't think it was hard, but there's a lot of steps there. So if you need to, watch it again. All right, moving on. Two positive charges, A and B, are placed at the corners of an equilateral triangle. What is the direction of the net electric force on charge negative Q? Okay, so let's look at this. We should know that in position A, that charge is going to be attracting it, and it's going to be attracting it this way. Okay, charge B is going to be attracting it this way. So the net charge is going to be a combination of both of this. So if we did it like with vector addition, it'll look like this, and the net force is going to look like that. So this is going to be net force going straight down because the x's cancel each other. The forces in the x direction cancel each other. Okay, so it'll be straight down. If that makes sense. Watch it again if it was a bit confusing. All right, two positive charges are placed at the corners of an equilateral triangle as shown. What is the direction of the net electric force on charge Q2? So again, similar kind of question, but different orientation of the positive and negative. So we should know that Q1 is going to be trying to push this Q2 going this way. And Q3 is going to be pulling it towards this way. So the net is going to be a combination of these two, where in this case, in the y direction, it's going to cancel out, so it's going to go directly to the right. Hope that made sense. That's everything. Watch it again if it didn't make sense. Next time, we're going to be not talking about forces as much, but we're going to be talking about the electric field. So excited to see you guys with that one. Thanks for watching, everybody. Bye.